So, this circuit is meant to be a biomedical signal circuit to acquire sound which are heartbeats from a stethoscope. The circuit contains a preamplifier, low pass filter, and also an audio amplifier.
ICTL072 is part of a preamplifier circuit. It is used to amplify the signal level of heartbeats that is taken in by the input of the stethoscope. IC1A is a low-noise JFET operational amplifier. C1 blocks the DC bias voltage from the input and reduces noise and interference from the power supply. Resistors R2 and R3 and also capacitors C2, C3 form a band-pass filter to only allow frequencies between 16 Hz and 1 kHz to pass through. Resistors R5 and R6 form a voltage divider to provide half the voltage into the IC. Capacitor C4 also blocks DC signals. For testing stage 1, I ensured DC power is set to 9 volts. As for the function generator, I ensured that the frequency is sine wave at 1 kHz at 200 millivolts peak to peak. To test, I placed probe of channel 1 of the oscilloscope to test point 1 and probe of channel 2 to test point 2. Throughout the testing, as you can see here, I slowly adjusted the frequency from 10 Hz to 4 kHz. As the frequency increases from 10 kHz to 500 Hz, the V out stops increasing at around 4.5 V and starts decreasing from there. Same can be said for the gain, which stops at around 22.5 volts. Now the frequency response curve shows that the minus 3 decibel line is 24 as I took the maximum decibel, which is 27, then subtract it by 3. From here, we can conclude that the lower cutoff frequency is 15 Hz and the higher one is at around 1.2 K. After finding the cutoff frequencies, we can start to find the bandwidth by subtracting the higher bandwidth, which is 1.2 kHz, and the lower bandwidth, 15 Hz. Then I receive 1184 Hz. ICT-L072 is used as a negative feedback loop amplifier, as the input is received from the inverted input at pin 6. R9 and R10 forms a voltage divider. P1 is used to adjust the resistance, which affects the input signal, which can also affect the gain and feedback of the amplifier. For testing in stage 2, which is TP2 and TP3, I ensured both frequency and power supply remain the same. I placed the probe of channel 1 on the oscilloscope at test point 2 and the probe of channel 2 of the oscilloscope at test point 3. As you can see, when I turn the trimmer, the waveform amplifies but eventually gets cut off.
Circuit 3 shows IC2A being part of a second-order Sallen-Key low-pass filter. Resistors R11 and R12 form a voltage divider to let half the voltage into the IC. It allows low frequencies to pass through, but does not allow high frequencies to pass through. C7 is used to provide feedback to shape the response at the edge of the pass band. C8 blocks DC voltage.
In testing for stage 3, I placed the probe of channel 1 at TP3 and the probe of channel 2 at TP4 to receive an output voltage around 5 volts. As I turn the trimmer, as you can see, the waveform will be amplified and eventually both waveforms will be cut off. Now referring to the frequency response curve, the -3 dB line will be at -3 dB. This can be found by taking 0 -3 dB. Hence, the higher cutoff frequency is 1.2 kHz. By knowing the higher and lower frequencies, the bandwidth can be found at 1200 Hz.
ICLM386N is part of a single supply audio amplifier. C13 is used to block DC but allow AC signals to pass. The potentiometer is used to adjust the signal of the waveform. C15 filters out frequencies above 40 kHz and allows frequencies below that to pass. The signal then reaches the speaker output.
In testing for stage 4, I placed the probe of channel 1 at test point 4 and the probe of channel 2 at test point 5. As you can see in the video, when adjusting the trimmer P2, the waveform at channel 2, which is test point 5, will be amplified into a sine wave.